Good morning, ladies and gentlemen. Welcome to this morning's plenary lecture. My name is Ian Craig from the University of Pretoria, and it's my pleasure to introduce our plenary speaker this morning, who's Paul Houpt. He's a principal scientist at GE Global Research. Paul earned his bachelor's degree at Syracuse University, and as a Bell Lab employee, he was sent to New York University to do a master's degree, after which he went to MIT, where he received his PhD with his thesis supervisor, Mike Athens, who's well known to this community. All in all, he spent about 15 years at MIT, first as a postdoc at LITS, the Laboratory for Information and Decision Systems, and then as a faculty member in the Department of Mechanical Engineering at MIT. Where he worked on vehicle control, wind power generation, which is pretty topical for today's discussion, and manufacturing process control for semiconductor materials. He left MIT in 1985 to join GE, and he's been associated with the automation and controls robotics at GE ever since. He's also a great servant to our community. He was an associate editor of the IEEE Transactions on Automatic Control, and he also served on the Control Systems Society of the IEEE's Board of Governors. He's also on various advisory councils and boards in the USA. For example, he's on the advisory board of Syracuse University's College of Electrical and Computer Engineering, the Strategic Advisory Council of the Institute for Systems Research at the University of Maryland. He has won numerous awards for his activities, especially at GE. He's an IEEE Fellow, and he's a true innovator, being able to take a product from the laboratory to a real product that makes money, because that's actually the definition of innovation. And at GE, he received the highest reward as being part of the team who developed a speed control for freight trains, which was taken from a concept to actually a product that GE makes a lot of money off. So it's my pleasure to introduce Paul Houpt, who's going to talk to us about smart grids and renewable integration, control challenges and opportunities. And I'm not going to read the abstract, but I just want to say that this work springs in part from an impact of control technology workshop that was held in Berchtesgaden in 2009. And to advertise a little bit, we'll have a panel discussion on that topic in this very room from 4 to 6 this afternoon. So for those of you interested in the broader scene, please come and join us in the panel discussion. And now, if I can ask Paul to give his plenary lecture. Thank you very much.
Yes. Thank you, Ian, for such a glowing introduction. And good morning to distinguished Ifac executives and to all of you here and in the other rooms. I'm sorry that you can't all fit in this room. The topic for today is renewables and smart grid. And I'm using this topic as a thread to try and tie together a number of different issues with respect to controls and smart grid. It's impossible to talk about everything, but I hope I will be able to give you a flavor for what the issues are. First of all, at the outset, I want to acknowledge I got a lot of help with this, and I've listed some of my colleagues at GE who are actively working with me in this area, and some people who recently retired, colleagues from energy, several outside of GE. And especially I wanted to thank the Smart Grid Workshop at the ACC. I've pirated a few of their slides, and I'm delighted to know of the great work that they're doing there. I'll say more about that as we go. As Ian said, the impetus for this, really the kickoff point, was a session on renewables and smart grid at the International Workshop on Controls in Berchtesgaden, which brought together industry and academic people to talk about the future of controls. I think this was one of the most stimulating meetings I've ever been to. It was fantastic having all these wonderful researchers from around the globe in one place at one time to talk about the future, and that's where we got started with this. Just a rough outline. I'm going to say a little bit about what is smart grid, a little snapshot of what it is today, talk about some of the control issues there, and zoom in on wind and solar renewable sources. And the principal problem that they present is integrating sources of renewables that are variable. If you were here for Peter's talk yesterday, we joked afterward that maybe I could just open and answer questions, because he did a very nice job covering the topic yesterday. But I think I'll have a few other things to say. The New York Times, in a op-ed in July of 2010, posited what would happen if Thomas Edison and Alexander Graham Bell came back on the scene today and observed the consequences of some of their inventions. Edison would see what looked pretty familiar. And of course, we have some considerable transformation in the telephone between then and now. I think we quip that this is not a quote, but hey, this looks pretty familiar. What's really new here? Well, I think, and whereas Bell would have noted that, wow, you can do all that and no wires too. So this was very contrasting public perceptions of what is new and different with respect to the grid. And what we want to try and explore here is what is different, what's new, what's exciting about this area. I want to say up front that there's a great place to go. The report out that Ian mentioned earlier will talk about smart grid. This picture is from this report out, and I put the URL down here at the bottom so that all of you with laptops out there can be prepared to answer hard questions or ask hard questions at the end about the subject. I also wanted to say very quickly, I could put up 100 names of people who you should read about what they're doing, but I picked 4 who I know. Masid Amin, who's sitting up here in the front right, Joe Chow at RPI, who's done pioneering work in modeling for power systems, Maria Illich. I don't know if she's at the conference, but has been a rock in this area for many years. And lastly, Praveen Varaya at Berkeley, who has done a lot of work in some of the stochastic modeling. So these are all faculty who have websites that you can Google and learn a lot about smart grid. And that between these two, you should be able to learn a lot. So to begin with, let's just talk a little bit about why we care about the grid. These are statistics. The amount of electricity is expected to grow by 2030, almost doubling. 40% the amount of greenhouse gas emissions for which electric generation counts. And 4x is the ratio of what it costs a kilowatt hour versus the cost of saving it through efficiency. So these are big drivers for what's out there, for why we are here today and at this conference. And many people are working in this field. The utility industry is facing unprecedented challenges due to carbon policy and green energy requirements, renewable portfolio standards in 29 states plus D.C., looking to get to 20 to 40% by 2050. Of course, energy demand is growing with electric vehicles and other sources. The cost of energy is not going down. There's an aging infrastructure out there and workforce. And so all of these, plus the increasing importance of quality of service, of electric delivery, are all big drivers for why we need to do things differently. The other big challenge, which I won't say a whole lot today, but is implicit in a lot of the work that's going on in controls, is the need for higher reliability. This chart that Masood Amin prepared for the IEEE spectrum in the January is indicative. The numbers aren't so terribly important as the trend, and that is that. And I think the question is, with respect to the outages and failures that occur, is can controls help? I think what are the real root causes and how do we get at that? We won't say a whole lot about that today, but those are questions that we want to begin to look at. So what is smart grid? If you ask 5 people what smart grid is, you'll get at least 8 different answers. But for me and for our discussion today, it's the electrical infrastructure that is the generation, transmission, and distribution system, combined with a communication and control infrastructure, which is trying to achieve a lot of objectives. And it can only achieve these objectives in a partnership with industry standards and a good regulatory environment that allows innovation and commercial entities to come in and supply into this space. So there are a lot of bubbles up here about things that we're trying to do, but I think these are the principal themes. That is reducing emissions, increasing efficiency, assuring that in a network with increasing demand that stability is assured, empowering consumers to be able to take advantage of variable pricing in some cases. We'd like to be able to get more power through the existing grid, of course, to integrate renewables, which is the main thing I want to talk about today. And these last 2 bullets, which I won't say anything about today, but are equally important, that is recovery from big disturbances and assuring that with all this intelligent equipment that we're putting out there and that we're not going to compromise security. So I've made a list of a long number of bullets here that I think many people, if you've been looking at this area, capture what are the goals of smart grid control technology, efficiency, renewable penetration, increasing power flow in the same network, and so forth. I'm not going to go through every bullet. It's clear these are tall orders. And the question before us is what's achievable, how will we do it, what are the priorities that we need to go after this, and at what cost? And while most of the data and experience I'll show today is for the U.S., clearly these are EU problems as well, not just in the USA. You have only to look at the mosaic of the players who are working in smart grid today, and in some sense it doesn't really matter what the axes are. The point is there's a lot of different equipment that's coming together, communications, control, optimization, all the stuff that this society, that Ifac and IEEE and ASME and AICHE and all the societies are working toward to be able to achieve the goals of smart grid. And we can hope that, we can certainly hope that there's a big pie out there if it's going to be shared this many ways. One other point I think is that the key issue here is interoperability. We need the standards to be able to get equipment to communicate. Without that, we're doomed to failure. There's big barriers in order to be able to achieve these goals. The system is complex. We have to be able to take the system and build on the legacy, which may be also complex and in some cases unknown. And we need to assess the impact of the return on investment from simple, e.g. maintaining equipment versus injecting new technology. Finally, I think a big barrier we have to worry about is the skeptical public and utilities about the regulators on the value of the innovations we're trying to produce with smart grid. And if this wasn't obvious that capital in the current economy, that finding scarce capital to invest in smart grid is a huge challenge. Why do we need to worry about consumers? Well, you only have to Google the word smart meters, and you will find organizations that are organized to try and slow down the innovation that we're trying to break. My only point of putting this slide up here is just as a slight caution that we need to understand as a society how to educate the public in terms of what we're about in producing advanced technology and be able to bring them along with us. They're stakeholders in this, and to deny that is not going to help our case. And that means collaboration across customers, academia, trade associations, and standards. And I've just listed a partial list of people that GE interacts with, but it's by no means exhaustive. The basic message is very simple. We definitely need to collaborate. So I'd like to just give a little grid snapshot so we're all on the same page about what we're talking about. Bulk generation of electricity is coming from a variety of sources. We talk about non-renewable, non-variable, renewable, and renewable that are variable. So wind and solar are the principal ones we'll be talking about today in this discussion. And the other dispatchable, so-called dispatchable sources are listed here. If we look at least in the USA, and I think the statistics in Europe may be similar in terms of where is power generated from, it comes from a lot of fossil sources, a little bit from renewables. At least in the U.S., more than half of this is hydro. And so the fact is that renewable is still a small penetration in the U.S. It's bigger here in the EU. Between Denmark and Sweden, there's a lot of wind power that is finding its way onto the grid. But the bulk of generation in North America is still fossil when we include coal, other steam, combined cycle, and combustion turbines. So when we talk about the grid, where this power is provided from these generation sources, this is what it looks like. And I stole this slide from Alexander von Meyer, and she has, this is pretty much shows the generation sources, the transmission system, the distribution system, and what you would see if you went out and walked the streets today. You would find these elements. And this is kind of how the approaches have been breaking down in terms of doing advanced control into these kind of subsystems. Control is coordinated at a higher level by so-called ISOs, independent system operators, or regional transmission organizations, and they're grouped in the U.S. As the picture shows here, and in the European Union there's a similar partition. The main point is that what these ISOs do at a top level is they coordinate, monitor, and control pretty much at a wholesale level power generation among multiple utilities. And that includes all the renewables, it includes fossil and everything else. And within a balancing area, their mission is pretty straightforward, to try and get to plan and schedule for power generation a day ahead in real time, sometimes a week ahead, for delivery at a certain time at a certain price. And the mechanisms for doing this market-based approach are very complex, and I won't say much about that today, except to keep that in the background as how things are being done. But when we think about power systems, including the management of the work of the ISOs, who are kind of on this end of the time scale, all the way down to, here's one, just for calibration purposes, here's 160 hertz or 50 hertz time frame. You end up with something in the order of 15 orders of magnitude for developing controls across the spectrum of advanced power generation. And the significance of this is that it's going to lead us to want to find ways to build systems that are hierarchical, take advantage of these separation of timescales to develop advanced controls. And to that end, let's just talk a little bit about transmission on the grid. The big picture is pretty simple. Make the power produced equal the power consumed. That in doing so, we keep frequency within tolerance, voltages are within tolerances, and that, most importantly, maybe, that they are stable to perturbations large and small. The reason it's hard, as I think many of you who have worked on this, the network is extremely complex, a lot of uncertainty. There are many complex and interacting operating constraints. The assets that you're trying to control are spatially separate, so the communication to try and coordinate them has latencies. There are limited knobs that you can turn for actuation, and we're going to talk a little bit about that in a minute to give a feel for what does it take to be able to get control of the grid. And finally, and as every controls student knows, that there's a lot of integer decisions to be made on unit commitments where you set tap settings, selecting capacitor banks, and so forth. And integers are no one's friend in controls. I don't think I need to talk about that. So the transmission going from bulk generation through various subsystems to the markets that you're selling it to, this is what we're talking about on the transmission side. Here, for example, in my neighborhood is a model of the so-called New York-New England grid. It's characterized by about 16 generators, 68 big buses, and this is kind of the nomenclature we use to describe buses. Peter did a nice job describing all of this yesterday. And the thing that is interesting about this, there are two big tie lines that link these two areas, and those tend to turn up to be interesting challenges. And there's also this gizmo down here. This is I'll say a little bit about this. This is a so-called fax device, electronically controlled capacitances. In this case, this particular device is inserted in this network because it turns out there are inter-area oscillations. Now, I'm not expecting you, I'm not going to draw you through every line on this diagram, but essentially this is representative of the kind of physics modeling that we capture in the way the system works, that to a large extent the dynamics of power systems are governed by two things. The transient dynamics that you see, the oscillations that occur most often, are associated with the prime mover, that is the turbine or generator or wind turbine that's generating power. And almost everything else, the voltages and currents and power flows, are nonlinear functions of phasor descriptions of the electrical network. So that essentially even though there are real dynamics because there are energy storage devices in here, these are typically assumed to be in steady state. There's a frequencies set points and power set points that are the kind of two inputs that come from a variety of sources. I'm not going to just go through all the excitation sources, all the control logic, other than to say that there are fast dynamics primarily that relate to voltage, and the slower stuff that relates to frequency and phase of the machines relative to one another. This work is well documented in many books, including Kundur, this nice book by Meliopoulos from Georgia Tech, which is available online. And I'm not going to. I wanted to have one slide just about the modeling. These are the equations. These are the famous swing equations. This is one model of a complex system. There are higher order models. There are a variety of techniques in which you can take description of an entire system, taking the topology of the interconnections together, and using a variety of very nifty techniques that I'm learning about from my colleagues at GE on graph decomposition, and going back to Joe Chow and work that's 25 years old on how to find the parts of the network that are sort of tightly coupled, which means in simple terms that these share pretty much similar frequencies, and you can represent these by a single pair of states. So that being able to, these are some of the techniques that are used, which if you've heard of these, they'll be familiar. If not, I don't have time to get into them all. But they are well tried and proven methods that are going to be used. Attacking a full-bore network of the New York variety that I just showed you is probably a mission impossible, that you need to do area reductions so that you can have models that are tractable. So, for example, when you apply common techniques to the New York model, it reduces to 5 areas, as I've shown here, and I'm not going to try and prove it. There are a bunch of different generators that are combined as one equivalent generator in each of these areas, and you end up with a model which is much lower order and more tractable for control. Speaking of control, I'm not going to go through every control strategy that one might apply in this area, but I want to mention, just thinking as a controls guy, what are the actuators that we have? Well, traditionally, there's been all the things that are over here on the left, things in substations like tap changers on transformers, switch and capacitor banks. and of course the prime mover in generation excitation. These have always been there. And there are now more electronically controllable AC transmission systems, which have a number of interesting characteristics. They can be applied at the transmission and at some substations. They're not usually found in the distribution systems, and they are used for system and transmission level problems such as damping interior power swings, modes that are produced by that are rooted to the prime mover. It is also possible to dynamically inject reactive power, which is used in voltage support, and power factor correction, very important attributes of real power systems. And perhaps the thing that gets me most excited about fax devices as they're deployed is that you can push power flow into underutilized parts of the network on a basis where it's necessary, and perhaps defer investment in expensive transmission lines. And lastly, the ability to have these new actuators to be able to move stability margins closer to the thermal limits is very important. I wanted to just show, we tend to think of actuators, here's the picture of what this would look like on a schematic diagram, and you're thinking maybe a rack worth of equipment. But in a transmission system, these things are enormous, expensive, and go in with great thought about what should go in there. These are vehicles on the bottom here to give you some scale. So these are important new actuators. I think they're give us a lot of interesting possibilities, and we'll be using those as we go. With respect to sensors, this is another important area of new information. Every controls engineer, if you can't measure it, you can't control it, except we had a big conversation about feed forward yesterday. There are some exceptions, but in general, it's important to do that. And one of the most important, in addition to the standard kind of voltage, currents, and power factor measurements, are these so-called phase measurement units, or synchrophasers. Being able to remotely measure what's happening in the system is important to do dynamic and as well as quasi-static control, but they have to be communicated across sometimes a very large network. And the thing that's cool about these PMUs is that they are GPS clock synchronized to great precision, so that it is possible, for example, as suggested by this picture, that you could get nationwide or large area views of how the phase angles are among machines, which can be indicative of stability. You can actually watch the propagation of these things under various kinds of fault conditions. PMUs and the associated measurements can be used together to be able to identify the dynamic modes, of which is a very common application that they've been used offline, both to identify which modes are associated, which modes are oscillating right now, what machine are they associated with, and then if I detect lightly damped modes, and Peter had some great examples of this yesterday, how you go about controlling them. So we have a suite of actuators and sensors that we can use, and this is just, I put Steinmetz's name up here. He was a GE guy. Maybe you didn't know that, but he is, and actually lived next door to me in Schenectady. But the angle between the machines is the primary thing that we're measuring and communicating, and is important to the swing equations and to controls that we want to develop. Finally, the other sensor that is probably the only way we're going to get line of sight to the end-use customer is smart meters. This provides information, can provide information in both directions about what's happening out at the load. It provides a means to rapidly detect outages instead of waiting for the phone call. And there's wireless ways to do it. This is where where the big controversies are happening, at least in the States. I don't know if that's happening here in Europe as well. But I think it's an important enabling technology for where we're going. I'd like to just switch gears. I'd like to just talk a little bit about wind and solar, and the controls associated with those systems. Of course, wind power, there are many manufacturers. I'll be showing just GE products for the obvious reason, but there are many great suppliers of wind equipment here in Europe and elsewhere. At least in the U.S., there's more than 5 gigawatts that have been installed. We're estimating growth to be 150 gigawatts by 2020, and that's a fraction of what DOE would like to see in the U.S. To achieve by 2020. A wind turbine, of course, has a lot of complicated mechanical components, and these have presented fairly interesting design challenges. When we start talking about really big wind power systems, this new 4-megawatt system that GE builds, and I'm pretty sure there are other manufacturers with similar things, intended for offshore use. The blades are 176 feet long. The rotor diameter is 360 feet. That's like, I think I calculated it's 2.5 747s end to end. The tower height is 300 feet. These things are big. And because they're big, the design of the control presents challenges both in terms of the flexibility of the rotors as well as the flexibility of the tower in highly varying wind conditions. So just a little bit about what the conventional wind generation. The earliest ones were fixed-speed synchronous machines just hooked up to the grid. There was no possibility to vary the speed. It had to be, if it was going to provide power, provided lots of challenges to make these things work. This is where I started back in the late 70s working on systems that were like this. And we've evolved to designs where today, essentially, we produce wind power where we can completely decouple the rotor speed from the frequency that's being provided to the grid, which gives us enormous flexibility and control. This is pretty much the industry norm as the way things are going today. Being able to decouple the frequency of generation and being able to control it with converters and inverters is a very powerful construct that enables control of energy that's produced. And I'm really sorry you can't really read these equations, but the main takeaway from this slide is that we can use state-of-the-art model-based and supervisory controls to build state estimation and controllers for the mechanical parts of the system, taking into account advanced aerodynamics and being able to produce the wind characteristics that are very predictable and friendly. With advanced controls based on a slightly evolving design, through controls we can reduce fatigue loads, which result from the interaction between the wind turbine and the tower itself, which are big flexible membranes. Very exciting area of advanced controls, and there are references to it in that IEEE survey that I mentioned up front, and be happy to, anyone who wants to send me a line, I'll tell you other references where you can read about these design techniques. Very exciting area. I'm not going to drag you through all of this chart about the way design is done, but the thing that's exciting to me about this in wind turbine design within GE is that for the first time, unlike controls, as many of you probably know, it's up there on the scale of painting the system for consideration in the actual design, and that is not the case in designing advanced wind turbines, where we can actually do things like use aerodynamic bleed and so forth to affect the lift structure in addition to being able to twist the pitch axis. And those considerations have impact both on the control and how it's optimized, the structural design, and the actuator size and where you put sensors to make these systems work. It's very exciting to be able to have these integrated control design techniques available to us. A few words about solar. I think the thing that's driven solar is increasing efficiency trends. There was another chart that was presented at the Smart Grid Workshop where there are literally 20 or 30 different suppliers who are working to get high efficiency solar panels. Solar is segmented into a number of different areas: residential, commercial, and utility. Most of GE's interest is primarily in the utility area, although we do play a little bit in the stuff that goes behind the meter. Typically on residential and commercial installations, there are less than 10 kilowatts in a typical applied system. They're supplying power into the distribution system. They have very limited central controllability, and yet they're going in because there's very attractive consumer incentives to put them in, such as the so-called feed-in tariffs, where you get 75 cents a kilowatt hour, which is maybe, at least in the U.S., about 10x as an incentive for you to install it on your roof. Maybe many of you have done that here. For the utility systems, we're talking about systems that are 10 megawatts and up and have typically 30 megawatts or so on the transmission side, but these systems that are 10 megawatts are even finding their way into the distribution system. And as Peter pointed out yesterday, the consequences of adding all these renewables, and particularly on the distribution side, is that protection and control equipment, which was conventionally meant for power going one direction, now has to protect in both directions. And there are some subtle and complex issues that has. But it's still a big segment. My colleague at the Munich workshop, Eduardo Camacho, had shown work in Spain on solar thermal, and that is another big solar area. But I'm not going to say anything about that today. It is just to point out that that's another means of generating solar. The thing about solar is it has relatively simple componentry. There's no moving parts except for the fans or whatever in the inverters, that you can take acres of these things, tie them together with the same inverters. This is what the inverter looks like for both wind and for use in solar. Slightly different software of how you tie these things together. GE is in partnership with various people to provide the cells, and are continuing to benefit from the technology evolution in solar as a basis for systems. They all are building on componentry like this, which is a great help. Here's what a typical PV wind farm, or what a PV farm or plant would look like. There are a lot of requirements that are needed, including I'll talk more about these in a minute, but essentially there are some grid-friendly features to be able to take solar plants like this and put them on the grid. Clearly, being able to aggregate power, the control strategies for doing this are well understood, and I won't say much about that today, that we can aggregate significant amounts of power, 10 to 30 megawatts, not uncommon, and be able to supply that into the transmission part of the network. If we try and look at some of the common challenges between wind and solar, there are some similarities and differences. They're both renewables. They've got a punch list of requirements to be on the grid. They're highly variable, difficult to forecast. Those are really the showstoppers for using them. Similar power electronics. And on the other hand, wind certainly has a lot more complex mechanical, electromechanical, and aerodynamic things, as we've shown before. Photovoltaic feeds both distribution and transmission systems. And on the other hand, really big wind farms really need to be tied into the transmission network. Occasionally they're not, but it's almost a necessity. In principle, because wind is typically further from the load than PV, which is likely to be distributed. But the thing that is most annoying, and I'll spend a lot of the rest of the time talking about, is the issue of variability in wind. There's things that are relatively easy to check off in terms of controls that utilities want. In some cases, they want power sources that are tying into the grid to have these so-called frequency droop characteristics, so it's sort of self-regulatory. If the frequency is going up, that means there's too much power going in. You want the system to be able to relax back. There are ramp rate constraints that are used in dispatch to do the control. Low voltage ride-through. This was a really huge issue in the early days of solar and wind. The reason being that we wanted the systems to be able to survive a short circuit, a temporary short circuit, and not go off. That is the primary requirement for this. That turns out to be a relatively straightforward control feature to add. And so these techniques have been developed over the last few years, and I'd say we put a check mark next to those as things that we can do. Still, the variability is out there. If we look at the wind and solar, there are variations there that essentially the averages are predictable, but on a day-to-day basis, they're not. And what do we do about it? There's a lot of work going on in trying to develop short and longer-term modeling strategies. These problems are all very hard. The more you know about what the load and the generation characteristics are going to be as a function of time, the more economically you can dispatch them, and the more likely you are to be able to assure stability and good control. But no matter how good the models are, you're always going to have a gap between supply and demand, and you'll have to do something with it. Elian Bitar showed this picture, and it shows kind of, well, I think the main takeaway you can see is that the average of this has lots of spread around what the wind might be over time. And these are significant variations. This is per unit, one, so you can have 20 or 30% variations in any given day, or worse, as this other chart suggests. So what do you do about this? Where do we identify the knobs that you can turn to try and recover control? Well, you can coordinate power flow into the grid from the, if you got lots of wind and demand falls, you can curtail power. You can use the forecasts if you've got them, but they're usually not very useful. You can increase generation if you've got stuff that can change quickly. You can exploit storage if it's available. I haven't said much about storage, at least for our business. Our concern is that the magnitude of the storage that you need is so huge. We're not sure it's cost effective with technology that's out there. We're still watching this, but storage is a huge thing. And I'll come back at the very end to show you the ultimate fantasy of storage in the context of a grid system. And of course, load modulation by either shedding load or using what's called demand response are all means to get back to a balance and essentially increase the supply, decrease the demand, either with fast procurement, with if you've got spinning reserves, which are set aside in the plane, reclaiming storage. There are techniques, which is a whole lecture in itself about using pricing, indirect pricing on this, and a very complex area I'm not going to say much about today. Rescheduling demand, such as with hybrid vehicles, that is replan if you don't really need to have the vehicle charged in the next hour, re-optimize to get it charged when you need to. Direct load control is a very exciting area that is in this category of demand response. I want to say a little bit about that because there's some exciting things going on there. And then there are places where we can make small changes to many loads. Now, I shamelessly put this, our newest Flex 50 combined cycle power plant. This is a big plant. This is not necessarily what you would need to have something to modulate, but the main takeaway is that this is a big, complex system that can start up quickly. 30 minutes is quickly in the scale of starting up equipment. You can ramp it up and down 50 megawatts a minute and can actually get 40% turn down from rated power and still be in compliance with emissions. So a very important class of technology, and I'm sure our competitors are producing similar things that fit nicely into trying to deal with variability with renewables integration. Now, demand response, to me, I think is a really exciting area because essentially it amounts to being able to not generate or consume anything, but essentially modulate how it's used. And I mentioned pricing, reschedule, and essentially it's within this matrix of things that are a complex range of loads. There are third parties like Enernoc who will provide a contract with you, the consumer. You say in a place like this college, tie in a bunch of loads together that when we tell you shut off, and becomes a very powerful tool for doing load control. There are limits to the frequency, the speed of which these kind of things can be response, but they're all part of the picture. And I mentioned before the rescheduling demand, but the one that really was exciting to me is rescheduling, making small perturbations to control systems. So Duncan Calloway at the Smart Grid Workshop mentioned some of the work that he's done. That's the first time I had seen it. What's so exciting about this work to me is that you can actually get with vary the production of power to match demand. This is the error in the demand that's being against the power that's required, simply by changing the set point of a lot of little plants that are out there. So in this example that he did, he simulated 1,000 air conditioning units in a conventional housing, in a residential setting. And the important takeaway is not how he did it, but the fact that you can make with very small set point changes, and this, for example, is the set point signal that this is in degrees C, the set point temperature for the space. These are basically, in terms of comfort, you would hardly notice it. And yet you can get enormous variation in power, in load that's produced. I think this is, and maybe this is known to many of you, but I thought this was a really exciting result, one which is an exciting area to dig much more deeply into, to be able to understand what other kinds of loads and things can we use to get this kind of control in which essentially the end load that's using this is still receiving the same quality of service that they had, and we're getting this great benefit in terms of being able to match supply with demand. Of course, to do this requires this two-way communication infrastructure, but we hope that will come soon. I'm not going to go through this in the interest of time. I'm not going to go through the sort of recapitulation of that. I want to just talk a little bit about go a little layer deeper into control strategies with renewables. And there's a lot of words up here, but essentially I want to focus on a system some people call these microgrids, but it could be a standalone system in which there's a mix of generation and controllable loads and uncontrollable loads and energy storage. You name your mix. Some kind of control strategy that coordinates, and it may or may not be hooked up to the grid. And the basic idea is that how do we find the optimal sequence to minimize performance metrics while meeting a lot of complex constraints. And where I want to take this, I want to bring this back. I want to show you the basic problem setup. You can get references from the references that I gave at the beginning to the details of how this has worked. There were some CDC papers that were written on the details of this technique and from the last ACC. But essentially the idea is with all of these knobs to turn in place and in particular integrating renewables, we want to think about this two ways. One is how do we manage this if it's an islanded standalone system, and as it becomes an asset to work with the grid. To develop this, we're using model predictive control. And as I think maybe many of you in this room, this is a workhorse that we've used in a lot of different areas. We use this in turbine startup and loading. We've used it I've used it personally in work in transportation railroad controls. Essentially starting with a model-based framework for the bits, solve a unit commitment algorithm, which is essentially the decision about how do we decide which units are to be operated, have some kind of prediction or schedule for what the loads and renewables are going to be produced, and then find set points for these aspects. That's a dispatch problem. Find the value of the benefits over a time horizon, and figure out what is the best way to match resources with with loads to meet your objectives. And I'm not going to give you a lecture about MPC, but the basic idea in this context is there's a unit commitment problem in which we solve this sometimes large integer program to decide which energy asset is available when, and that will meet equipment constraints. Then, given the available assets, we solve a dispatch problem. And this can be an LP, as I've suggested here, or it can be a QP, in which the network flow constraints, all of this is typically solved in a quasi-steady state framework. That is, this is describing evolution over time of a system in quasi-steady state. So think of setting all the set points for all those generators in the face of this varying demand, but essentially it's a quasi-static problem. And as in lots of MPC frameworks, you solve this problem over a horizon, typically 24 hours. You solve the problem for the 24-hour horizon, and then over some time interval, in this case, the problem I'm going to show you, 6 minutes, you resolve the problem again to account for all the new things that have happened. And here's a typical example of a system we built in a remote part of Canada. This is actually a completely islanded system. It doesn't even. This is the grid. It's all in one place. It consists of various loads from various sources of energy, from hydro, from diesel. There is an electrolyzer and a fuel cell for generation and conventional batteries. And essentially, to control the system over a 24-hour time horizon, if you set the problem up and come up with a solution, you are looking at a time scale, sample times of about 3 minutes, and this optimizer running every 6 minutes, predict ahead an hour. And the main takeaway from this is the number of variables in the solution and the inequality constraints. And we did simulation results over a variety of initial conditions and so forth, and it is something that can be solved fairly quickly. So in this case, with not doing anything very fancy, this system primarily uses diesel. We were able to save 12 or 13%. I should caution that this is not a typical percentage saving of fuel in most smart grid applications, but one that's at least encouraging to go off and try and do this. And the future of where I think this is going to, or one that I'm excited about, is how do we scale similar kind of ideas in a hierarchy. So in this case, the framework is, if you think back to the New York-New England network where we divided it into sub-partitions, we add to those partitions PMUs, provide communication up through local multivariable controls, which would provide, for example, the stabilization, and then do the MPC at a higher level where we coordinate all these set points. And I can't prove it to you today, but we are in the process of building systems like this and building it on fairly powerful tools that we are excited to be rolling out into this domain, building on stuff that we've done for a while. We are still working on how do we formulate and solve these multivariable problems to achieve stability. It's a great area. I hope if you're looking for PhD theses that you'll find some things to work in this area. I think what I'd like to do, rather than recapitulate everything that I've said, I'd like to show you a short film. And now the context for this film is really an area that was exciting to me, which is to try and take a lot of the ideas of smart grid. If we project it out into the future, imagine that we had plenty of storage and tie it back to what I spend a lot of my other time doing, which is transportation-related things. This is what the future might look like. I want to show you the film, and then I'll have a few comments about that.
It's nearing 7 a.m. and Rail's distributed generation assets begin operation. The grid's peak load begins to build. An electric car is fully charged, ready for the journey to the station. Soon, the Rail Grid control room starts to show specific energy capacity constraints. And trains are switched to coast mode where capable.
Not sure we'll be able to do that.
The car parks and plugs into a charging point. Stored energy trains top up charge in the station, and additional charge is supplied by electric cars and wayside storage where possible. The stored energy train pulls away from the station and traverses onto a non-electrified rail section. During the day, wind and solar assets on rail land provide renewable energy to the grid, whilst other distributed generation operates in conjunction with grid supplies as the power market dictates. In the late afternoon, surplus freight locomotives dock to special national grid nodes for peak support services. Electric cars and wayside storage again provide peak support. The electric car returns home and couples to the smart charging point for deep charge overnight. Stored energy trains return to the depot for an overnight deep charge on the rail overnight tariff.
So here's the question. How many modes, how many times was energy changed? How many control systems were involved in that system? And if you come up with a count and get it correct, send me an email. And that's a little unfair because you don't have it in front of you to see. But this will be recorded so you can play it back, and I'd love to hear from you. To conclude, I think what I'd like to do, since we're out of time, I just wanted to say a few remarks. We haven't talked a lot about benefits in the context of advanced controls. We've broken this down into a lot of different areas, and these numbers aren't important. I'll make these available, this particular chart available as part of the presentation to look at in detail. This is an area where we as a society need to pay attention as we're developing these advanced control concepts and going out into the marketplace to what is the benefit going to be to the utility, to the consumer. We have to articulate that. We have to be able to prove that these benefits are real and come up with how controls is going to help us. Controls is part of everything except this prognostics and diagnostics, and some would argue that the models that we use even fit into that space. So controls is very important in the future of the smart grid. I think it's a very exciting area to be working at. I think if I would say that if Thomas Edison were to come back and see all the exciting stuff that's going out there, I think he would be quite hopeful. But he would probably ask, how much is all this going to cost? And that's it.
Thank you very much, Paul, for that thought-provoking presentation. Making grids smart and also integrating renewable energy sources into the grid is, I think, a very topical area also for our community, in which we can and are playing a significant role and maybe even a pivotal role. So that's a challenge for our community to make its technology felt in this area and bring it to the forefront, that it's not the so-called hidden technology that we always talk about. We appreciate very much the effort that goes into preparing a plenary lecture like this, and we'd like to thank you very much for your presentation. So let's give Paul another hand. Thank you. That then concludes this plenary session, and I'd like to thank you for your attendance. Thank you.